Good morning, everyone. My name is Yipei. I'm a PhD student from Huazhong University of Science and Technology. And today I'm very glad to be here to present our paper, which is titled PostMan Rapidly Mitigating Bursty Traffic by Offloading Packet Processing. It's known to us all that sudden events such as news in a spotlight on a social network or hot items in a shopping season is becoming ubiquitous. And such sudden events always brings unexpected bursty traffic. And based on a statistic of Akamai and Alibaba, the conversion rate on Cyber Monday increases 35% in 24 hours, and orders at the peak on Double 11 Shopping Festival exceeds 32 million per second. And such bursty traffic can cause severe load imbalance in backend services. And some of these services, such as Memcached, are processing small requests. For example, Facebook reported that in its caching layer, most key sizes are under 30 bytes, and median value size is 135 bytes. And processing such small packets would incur a very high overhead. So the standard approach to mitigate load imbalance caused by such sudden events, caused by such bursty traffic is migrating hot data to less busy servers. However, migrating hot data is time-consuming. Furthermore, it will inevitably slow down the server that is already under heavy load, and the high packet processing overhead still exists. So Amazon Dynamo runs data migration at the lowest priority and finds that during a busy shopping season, data migration can take almost a day to complete. So we propose PostMan, an alternative approach to rapidly mitigate load imbalance for services processing small requests. And PostMan deploys a number of middleboxes called helpers to adaptively batch small packets into large ones and send them to the heavily loaded server. As a result, the packet processing overhead is offloaded to the helpers on demand. So, benefiting from the above features, PostMan is able to avoid data migration and achieve rapid mitigation. So, to batch small packets, we need to first discuss how these small packets are assembled. In a helper node, when a packet is received, the TCP, IP, and MAC headers will be replaced by a PostMan header. Such a PostMan header is a 3-tuple structure. First tuple is a 1-byte identification code that identifies the type of the packet. And the packet can have one of the following 3 types: a request, reply, and connect. The second tuple is a 2-byte length field to record the length of the payload. And the third tuple is a 4-byte long, which contains the source IP and port of the payload to locate the sender. And the helper extracts the lower 16 bits from a source IP and then hatch them into a 2-byte identifier, which can cover less than 64,000 machines for a modest scale cluster. So after defining the PostMan header, we then present how these packets are batched in helpers. So to efficiently process these small packets, we implement PostMan with DPDK. And upon DPDK, we use MTCP to handle TCP protocol and connections. Hence, the packets can be processed efficiently with this fast I/O technique and user-level network stack. As such, original packet headers are replaced by PostMan headers. And helpers will batch the small packets that have the same destination IP and port into a large one and send it to the heavily loaded server. As a result, duplicated headers are replaced to alleviate packet processing overhead. So PostMan leverages per-core thread and independent per-core contacts to avoid synchronization among different assembling threads. So by now, everything seems fine except the helper node fails. So if a helper node fails, It cannot provide enough information for packet retransmission. Under such a scenario, we are supposed to migrate connection from the failed helper to another one and resend the packets. In Postman, we choose to redirect requests to another helper node. And the redirection approach brings lower overhead, but it requires the faulty node to be stateless. Namely, it does not have any important states that will affect the execution. So here is our solution. Supposing that our memory cache is under heavy load, and the first 4 packets are sent, and the server receives the first 3 packets. And when a helper node fails, the client will connect to another helper node, and then sends a reconnect message to the server through the new helper node, which contains a number of sent and received packets at the client side. And when the server receives such a command, it will stop receiving packets on old connection, and it will respond with a packet which contains the number of sent and received packets at the server side. So by exchanging the number of sent and received packets and comparing them to the offset of the buffered packets, and both sides can determine which packets should be retransferred. So as a result, Postman can migrate connection freely across helper nodes, and these helper nodes are highly scalable because of stateless natures. And to support the above functionalities of establishing connection, assembling and disassembling packets, Postman library provides a few additional APIs, and like connect, decompose, and compose, and get info. So a developer should use these additional APIs together with traditional APIs to build the applications. So after presenting the above implementation details, we then make summary of how Postman works in practice. First of all, we need to answer a question for Postman when to connect to helpers. Supposing that the server is under high load, and then the client the latency in the client is detected to be higher than SLA. And in Postman, the clients will decide to disconnect from the server and connect to the helper, which brings the minimal overhead to the server to the server side. Then the clients are required to select one helper node to connect. And the strategy of selecting helper node in Postman is as follows. And each helper will monitor its CPU and network utilization. And when the client establishes a new connection, it will select a number of helper nodes. And these helper nodes will reply with their utilization resources so that the client can choose the helper with the lowest utilization. And in this case, the upper one is chosen, and the connection can be built, can be established. And when a helper finds its resource utilization is too high, it disconnects existing connections so that corresponding clients can connect to other helpers. So the upper one is overloaded, and one connection is migrated to the other one. Finally, we should decide when to disconnect from helpers. On one hand, since clients cannot gain the overall load of the server, so it might not be able to make the best decision. On the other hand, a server certainly has more information to make a better decision, but to execute the decision, the server must pay the overhead of notifying the corresponding helpers and clients, so which could be problematic if the server is already under heavy load. As a result, in Postman, when the throughput of the server is become normal, And the server will decide to disable helpers and notifies clients to establish direct connection to itself. And the overhead is fine in this case since the server is not too busy. Now, we clarify the positioning of PostMan. So PostMan is designed for app-wrapped load imbalance. So migrating data in this case may take much longer time than PostMan and may waste resources if the load imbalance disappears soon. So if the load imbalance becomes stable and predictable, and the migrating data can finally solve the load imbalance problem, and the PostMan can be disabled. So PostMan and data migration are complementary. And here listed the evaluation or evaluation setup. Our evaluation is conducted on a cloud lab with 15 machines, and every machine has 10 physical cores with hyper-threading. And the specification of software in the clients and helpers and servers is listed here. Finally, we set the SLA as 500 microseconds, and it is a 99th percentile latency. So compared with data migration, and PostMan can mitigate bursty traffic within 550 milliseconds on memory cache and 750 milliseconds on pixels. And PostMan can improve throughput by 3.3 times on memory cache and 2.8 times on pixels, respectively. And to quantitatively understand how PostMan's capacity is affected by the packet size, and we use ping-pong micro-benchmark to measure the throughput of PostMan. And on Linux, the turning points are 400 bytes and 1,460 bytes, respectively. And on IX, the turning points are smaller, 260 bytes and 920 bytes, respectively. And to examine the failure recovery of helper nodes, we first let all clients connect to one helper and record the throughput of the clients and manually kill the connected helper. As shown in this figure, the reconnection takes about 0.4 milliseconds to recover all 1,000 connections. And finally, we conclude our talk. We propose PostMan an alternative approach to rapidly mitigate load imbalance for services processing small requests. And PostMan is rapid, which is faster than the data migration, and it is efficient when processing small requests, and it is fault-tolerant for its stateless nature, and the PostMan helper nodes are highly scalable because it has no scalability bottleneck at all. And here listed the reference in this talk, and that's all. Thank you. I'm happy to take any questions.
Hi, I'm Harshit Gupta from Georgia Tech. I have a question about Memcached. Since I think that the request would be a lot biased towards reads, the workload would be read heavy. So in that case, can't an alternate approach just migrate the request to another Memcached server, which can then fetch the data from the backend and then start serving requests to the clients instead? So it would be like layer 7 load balancing instead of deploying this user space packet processing application.
You're asking how the data is migrated from the one Memcached to another one?
No, I'm saying maybe in Memcached you don't need to migrate data. You can just replicate the cache data on the other Memcached server from the backend and then load balance the requests, because it's a read only. It's a read heavy workload.
You mean the data?
Yes.
So the migration is to migrate the hard data from one overloaded server to other less idle servers. So other servers, they don't have the hot data, so it must be migrated from the overloaded server to other less busy servers.
I guess the assumption is that there can be only one copy of data across all the servers.
Right. But we cannot make one data copy in advance. So if the data becomes hot, so we have to migrate when traffic grows, increases.
Thank you.
Thank you.
Ed Bugnon, EPFL, interesting talk. So I buy the fact that you can increase the good put, right? Because you eliminate headers, you eliminate redundancy, and you coalesce packets. The question is, how much does it cost? And if I understand your evaluation, one postman can cover 6 servers, right? Is that correct?
One postman cover
about 6 servers.
No, not like that.
No.
Yeah.
No, maybe I didn't understand what you evaluate. How many Memcached servers can you put behind one instance of Postman?
Okay, we actually didn't matter how many backend servers that the helper could handle. So we just measures how much data volumes, like throughput, that a Postman can handle.
But that's your cost metric, right? Your cost metric is rather than having, let's say, 10 Memcached servers, right? You can increase the throughput of these 10 Memcached servers. I buy that. That's good. But that has a cost. And the cost is for these 10 or 100 Memcached servers, you need X additional servers. And that number feels high.
Sorry, sir. You mean the helper is one additional server, right?
Absolutely, yes.
Yeah, because you mean maybe it is not a big. It's a waste of resource. You mean adding a new helper server right there, right?
Well, it's a cost, yeah.
Yeah, I mean.
So and my question is, what is your cost, and how did you measure it, the cost?
Okay, sure. Actually, when the burst traffic arrives and the data migration will so to mitigate such bursty traffic, the data migration will be time consuming. So you don't have enough time to handle such bursty traffic. So you have to use helper node to mitigating such bursty traffic. So first of all, the resource is inevitable. So
No. You increase the throughput. That's the benefit. You need to have additional resources. That's the cost.
Yes, right.
Yeah. Okay, thank you.
Yeah, I wanted to make sure we have time for our last question. And could our next speaker get set up while we're answering this question?
Okay, Same from MIT, good talk.
Yeah.
So I'm just wondering, what you are basically trying to do is try to merge multiple network packets into a single big bucket and send to the server. So have you also considered like to merge multiple application requests? For example, hey, you are getting multiple GET requests from multiple clients. So actually you could merge them if they are actually hitting the same hotkey, or you are getting multiple like put requests. They are also hitting to the same key. So actually you can merge them into a single request and send the last put request to the server. So have you also considered this kind of merging? I'm assuming it could further help you to improve the performance.
Sorry, please be slower.
Okay, so have you also considered try to merge the application request? So what you are trying to do is to merge the network packet, right? So
okay,
in many cases, like application requests could also be merged. So you could basically reduce the number of final requests that's sent to the server, right?
Okay, I mean, why not just merge this request in client side, right?
No. In your middle postman.
Oh, right. You mean just an application layer that merge these requests?
Yeah. For example, for Memcached, there are lots of like hotkeys. So basically, you are hitting the same key. This gives you a space to merge those requests into a single request, right?
Right. I think that is interesting, but I think Postman is focused on the improve the throughput of in the link. So maybe we can add this. Maybe it's another good idea to solve this problem.
All right. Let's thank our speaker again.